that we have for this particular clustering. Okay, the very first, starting from the first one, you have a fraud or a what we use as spam clustering, okay, in our email boxes, okay, that one. The second one, biological data, phylum, taxonomical classifications which have been used. The third one, city planning, based on the identification, you get property indexes. Do you get property indexes on Times of India? If people are going through, what's the value of the house that you are in this particular area? Yes, every week you get an update on it. Climatic change, ocean temperatures, atmospheric temperatures on Earth's climate, finance, stock market clustering, the indexing of stock market, image data. Next you have information retrieval, your Google News, the land usage. Okay, how do people say that agricultural land is nowadays converted? This much of percentage is getting converted. Is there people sitting calculating? No. Data comes in. Okay, data comes in and clustering happens. You have market segmentation, and the last one you have social network, where you now have the special interest groups forming up, not only your friends. Now mutual friends are not only your own friends. Anybody who has your own mindset is also getting framed. We are bringing it to a quotient which is called as effect computing. Emotion recognition of a person, and they try to map that particular content. Now these are a few applications, okay? You can relate any of the applications to the approaches and the algorithms that we are going to take forward, okay? So as I told you, the levels of supervision we are clear, we have finished that. Now I'm going to drain into 6 different approaches that are basically there for clustering algorithms, okay? The most popular or the common approach that we have is called as partitioning approach. I think most of them would have used K-means algorithm. At least for us to learn it, the first step of clustering would be using a K-means algorithm, right? So you try to find a measure on the clustering that you have done. So you divide the data set, okay? The division happens based on some criteria. You have an objective function, you maximize it or you minimize it, right? That is what is called as partitioning approach. I hope I will not go further into it. You have a lot of versions of K-means, K-medoids. We will be seeing a few of them. The next one is called as hierarchical approach. Okay, this hierarchical approach, you could see, not only on the term of basic clusters, okay, the final result of clustering is always not number of clusters. Hierarchical cluster is one such example. You get finally a single cluster, okay. That's basically the behavior of the data. It is all together a single cluster. In the single cluster, you find subclusters in it, right? But the approach is divisive in nature. It doesn't go as a ensemble method. It goes as divisive. So I have data, I keep dividing. Once I divide 2 clusters, I keep grouping them together. It becomes your hierarchical tree structure that we have already seen in your data structures. So this is one cluster, this is one cluster. I find the cluster similarity, I group it into a single cluster. Okay, so all together at the end of the day I get one cluster. Okay, the point where I start, that is the approach. Okay, the next approach is density based approach. See, we now have lot of spatial data available to us. Okay, there is no point in talking about single dimensional data that we have. We have multi-dimension data. Okay, so we need some density functions to define a data point on a space, on a data space. That is what we call as a density based approach. So we are not only going to think about a data point in one cluster. The data point's attitude towards other data points in the cluster. That is what we call as density based clustering. Okay. The next approach, we have model based approach. See, we generally always have this statistical and mathematical models as our base. Okay, if we can hypothesize those models and fit our data into those models, the behavior is very good. So there are mathematical proofs that has been given. If we go for a model based approach, we would be able to prove that the data behavior is the same as in practical. Okay, there are a few algorithms, the Gaussian methods, mixture models, and cobweb algorithms, which falls into this category of clustering. The next one is called a spectral clustering approach. Okay, it's basically trying to form a graph with the data set. okay, and try to get subgraphs out of it, find graph density functions in it, and then make a cluster out of it. Okay, this is called as spectral clustering approach. If I can visualize data as a graph, okay, make spectral cuts. One very good example or a common algorithm which is used is normal cuts. Okay, people who have already used it will know the message of how do we cut a graph as a subgraph when we connect. Okay, the next approach is, of course, we have this ensemble method, or in very basic terms, a hybrid model. When we take a data set, generally a data set does not consist of only numerical values. We always nowadays get data set which is categorical in nature, which is nominal in nature, which is not normalized. You get different data values in a data set. Okay, now how do I approach that particular data set? Okay, my k-means will surely fail because it's going to work only with numerical data. What happens if I have a categorical data? I can give you an example. We have seen healthcare data there. In a healthcare data, a column having blood group is surely going to be a categorical data. It's going to say A positive, B positive, O positive. I cannot make it into a numerical data. Okay, and I cannot go in for a coding also. I can't say A positive is all ones, because this is going to be plotted on a space. Right, so it's all going to be on a single point then. In those cases, we are left with methods called as ensemble, where we can have more than one approach combined together. Okay, there I have just combined 3 k-means algorithm and shown you all. Okay, this k-means can be substituted with any algorithm there. Okay, that is an ensemble approach. Okay, the next one. I hope these approaches are clear. Okay, so we are given the data, we have seen the data, we have decided what supervision we are going to adapt on them. The second one, we have decided on what type of approach we are going to follow based on the behavior or based on the content of the data that we have. Okay, now we will start off finding out what algorithms are available, which type of algorithm will be suitable for which type of data. Okay, as a base point, I would like to start up. These are a list of unsupervised learning algorithms that I have quickly made. Okay, I hope you have heard all these algorithms. A few of them have implemented all these algorithms. Yes. We will move on to the first one. It's called k-means clustering. Okay, so I have only done half the steps of the algorithm. Okay, I have not given full steps here. Decide on the value of k. K is supposed to be the number of clusters. Okay, so people, if it's difficult for you all to follow, you can tell me. We'll take a practical example and then go by. You want us to take a practical example, or shall we go by the algorithm? Example. Okay. Now I'm going to take a data, okay, which has to be clustered, something like this. I am taking the income data of Bangalore. Okay, every person, every individual working in Bangalore has income, getting an income. So I have that income data. So I have the number, the employee ID of the person, the name of the person. I have the income that he is getting, his age, and so many things. Okay. Now I want to give this data to my k-means algorithm. Okay. If I have to give this data to my k-means algorithm, this k-means algorithm requires a value called k. Okay, this k is the number of clusters I am looking for, or number of partitions I want in the data. Now I want the data like this. I want people earning less than 12 lakhs per annum. Okay, that is 1k. Okay, people earning from 12.1 to 40 lakhs per annum. This is another cluster. So I am planning to try and cluster. Basically, k is nothing but, in terms of supervision, it's the label. It's the class label that I want to give for the data. Okay. So if I have to give this k, I should know how many clusters I need. So it's a prerequisite of the algorithm that I mentioned this k. I hope it's clear. Yes. So I have to give k as my input. The next one, I am supposed to give the k centers. Okay, I am supposed to initialize my k centers. The blue dots that you see are my data points in the graph. Okay, I am initializing 3 mean values. assuming that my k value is 3. I want to do a 3 cluster using my k means. Okay, I have to find 3 mean points for this algorithm. Okay, usually it is done randomly. Okay, usual process is this k1, k2 and k3 is done randomly. Okay, now after I do this k1, k2, I start trying to find the distance of that mean from each data point. Okay, this is the mean, this data point, the mean is almost the same, I cluster it. So I get 3 clusters like this. Every data point I find out to which point, which mean it is closer, I bring it to that cluster. Okay, I have 20 data points, I have 3 means. I will take one data point, find out it is closer to which mean, put it in that cluster. Is this clear? Yes? So this is my first level of clustering. The next level, now there is a new data point which is come and sitting inside my K2 cluster. Now the mean has to be recalculated for the second cluster. As I add each data point into the cluster, I am supposed to recalculate the mean. So the mean also keeps moving. So I get a better cluster. I hope it's clear. I'll reiterate if you want. I have a set of data points. I assume 3 mean values. Okay? These 3 mean values, I take every data point. I find out, okay, data point 1, it is mapping into cluster K1. Okay? Into the mean point K1. K1 will be recalculated because this new data point has to have an effect on that cluster. Is this clear? So I'm going to reiterate until there is no change happening in my, I'm going to reiterate this entire process until all my data is going to fling into one mean. That is how we call this as a k-means algorithm. I hope k-means is clear. Yes. Okay, this is a very popular algorithm, but there are a lot of advantages. I can talk one full day on what are the advantages of k-means. Okay. But there are a lot of disadvantages of k-means. That is what is paving way for so many other algorithms to come into picture. Okay, so what are these problems that we have? Number 1, as we've already discussed, categorical data will fail if I go to k-means. Because it's all numbers, right? What I'm plotting on the graph is all numbers. And I'm working on the mean value, which means I need a numerical value to calculate the mean and bring the data points into my cluster. Surely categorical data will not work with k-means. That's the first problem. The second one, handling noisy and outlier data. I hope noise is very clear. Okay, noise I will term it as negative examples or negative data in my data set. Okay, but what is this outlier? Okay, there's a huge debate. Should we consider outlier or should we leave outliers? Okay, but my personal preference is we have to consider outlier. Okay, in the same income data that I have already told you, the example that we are using, there is always a person who is not into these clusters at all. My starting cluster starts only with 12 lakhs per annum. There are people who are lesser than 12 lakhs. There is a skew distribution there. Okay, and there are people who are on the other end also which may not cover. These people are called as the outliers. But surely when I make a mean on the Bangalore data set, they have to be accommodated inside. For any plan that I'm going to make, they have to be. So if I leave out the outliers, I will not have a proper structured data. So outliers are mandatory. Outliers, to be quickly defined, they are extreme values in the data set. They are either very less or they are either very high. They are called as your outliers. Okay, so k-means is not that very good in handling these outliers because it takes only the mean. It takes only the closer mean. So the outliers will stay there only. They will not get into any of the means. They will be there. The lesser values and the higher values are going to be staying on the graph wherever they are. Okay, so k-means cannot handle that. The next one, I am supposed to specify the number of clusters. That is a very tricky work here. Okay, I have to specify k. Okay, without knowing the data, I have Bangalore income data. If I specify 3 clusters only, okay, do I do justice on the clustering that I get? No. So knowing the k value is not that easy. So I need an algorithm which will work without taking the k value, which is going to automatically do a clustering on its own. Based on each data it gets, it should do a clustering. So k-means will fail because I need to give a k cluster. If I don't have a knowledge of giving that number of clusters, I can't use k-means. Okay. The next one, we have some shapes called as non-convex shapes. Okay. If it is a convex shape, it is very easy to find the clusters. Okay. Non-convex shape is very difficult for me to find the clustering. Something like this. If I have my data points plotted like this, okay, actually I have data points, I have just drawn the major fit line there. Okay, if I have my data points like this, how would you like to see your clusters? Your cluster should be like this, yes, and the other one should be like this. This is what is called as an appropriate clustering. Okay, now my k-means, if I apply, I will get one cluster here, I will get one cluster here, I will get another cluster here. Because I am doing a mean. I am doing a mean of the values. So such non-convex shapes, k-means will not be able to handle. Okay? And at the end, you have this problem of local minimum. You are always trying to find a mean of only that local area. Okay? There is nowhere that global data is coming into picture. So always it gets stuck on a local minimum if the data is so. Many times we don't get a local minimum on the data sets. Okay, so these are supposed to be the. Yes.
So it can detect clusters which are convex.
It can detect clusters which are convex.
So it is convex, then how can it get trapped?
Convex is supposed to be a structure which is, say something like this. I have something like this. This is supposed to be convex or non-convex. Supposed to be a non-convex structure.
Because we can't draw a line.
We can't draw a line. Very simple. I have to have a linearly separable data for doing a convex. Right? I can't do a linear separable line here. I have the data like this. See, how do I differentiate? Just to quickly run upon what is the question is, if I have a data, if I plot the data, if I can draw a single line and differentiate the data into two parts, then I say that as a convex data. Linearly separable. They are linearly separable. I draw a line, it gets linearly separable. Anything which I can't draw a line, see this particular data, can I draw a line and separate? It's not possible with a single line. Then I say it as a non-convex data. This non-convex data I can't split up. Okay? So when I have something which is non-convex, looking convex, okay, unless until I plot it, I will not be able to find out. Okay? Because this data is very huge. I deal with huge data. Unless until I do the clustering and find out on the plot, then only I understand it is non-convex. In that case, it will get stuck in a local minimum.
But if we are having a convex, it is guaranteed.
Guaranteed to find. Convex k-means will work. It will work. It will converge also. Even though there is no mathematical proof that k-means can converge. Okay, the proof that they have, that mathematics people have is k-means has not failed with any convex data. So it converges. That is how it is. Okay. So these are the comments or these are the drawbacks that we have with k-means. Okay. Now we are going to look into different algorithms which will overcome these of all these. Okay. So the very first one for categorical data. Okay. I would suggest the very simple variation of k-means which is called as k-modes. Okay. As mean is a statistical measure, mode is also a statistical measure. Okay. I hope all of them know what is a mode. Yes? Should I get into it? Mode is supposed to be a highest frequency value. Okay. Supposed to be the highest frequency on a data set that I have. Okay. So instead of finding in the algorithm only changes, instead of calculating mean and reiterating that K1, K2, K3 as means, K1, K2, K3 will be my mode values. I will keep reiterating based on the frequency of the data that I have. Okay? Okay, how does that work with my categorical data? I have A positive, B positive, O positive in my blood group. The frequency of the occurrence of the data is going to be my numerical values. Do you get it? Yes? It's another way of looking at my categorical data into a mode value. So it becomes a numerical data, and I'm going to try to reiterate without mean a mode value on it. Okay, so practically it is going to drain down or solve the problem of categorical data, but still we are left out with two more problems. K modes also requires the number of clusters to be specified prior to the algorithm. The local optimum is still there. I don't get global information there. Okay, so a suggestion is, if you have a categorical data on a column, you can take an ensemble method where you have first a k-means for only the columns which is numerical. For the last column you do a k-modes, merge them, you have a solution in hand. Okay, that is how you can approach a particular data set with k-modes, which has a single column of categorical data. Okay, the next one, how do you handle noise and outliers? Okay, generally, no, in literature and in many works, okay, commonly they do two things. Okay, that is what I have listed in the first and the second. Okay, the first one is you remove them out. You find the outliers. You do k-means, whatever is not in the cluster, you take them out. Okay, assuming that the data is enough for you, which is clustered. Okay, or assuming that you are on more of a positive side of example.